Hello everyone, welcome back to quantum computing session. Today we will start with the exciting question. Have you ever wondered why computers keep getting faster every year? But yet experts now believe classical computing may soon hit a wall. And if that happens, what comes next? So in this session, we will check why classical computers are slowing down, how each transistor limits become a problem, and why technologies like quantum computing are suddenly becoming so important. Right now, almost every digital device around you depends on classical computing. Your phone, your laptop, gaming consoles, cloud servers, even massive internet platforms, all operating using the same basic idea. Tiny electronic switches called bits process information using zeros and ones. It sounds simple, but this system built the modern world. Think about this for a moment. Streaming videos, online banking, artificial intelligence, GPS navigation, social media, none of this would exist even without classical computers. For decades, engineers kept improving these systems, making them smaller, faster, and more powerful. And honestly, it almost felt endless. Every few years, device became dramatically better. But now something interesting is happening. The progress that once felt unstoppable is beginning to slow down. Why? Because modern technology demands are growing faster than classical computers can comfortably handle. AI systems now process enormous amounts of data. Scientific simulations require unbelievable computing power. And as we continue pushing these machines harder, we are starting to discover that the physical world itself may be placing limits on classical computing. The rise of computing power over the past few decades has been nothing short of incredible. Imagine someone using a computer in the 1980s and then suddenly seeing today's smartphones. The difference would feel almost magical. Computers became smaller, faster, cheaper, and dramatically more powerful. This happened largely because engineers learned how to place more and more transistors onto tiny computer chips. A transistor acts like a microscopic switch controlling electrical signals inside processors. The more transistors engineers could fit onto a chip, the more calculations computers could perform every second. Now imagine shrinking millions, then billions of tiny switches onto something small enough to fit in your hand. That's exactly what happened. This rapid improvement transformed industries across the planet. It accelerated medicine, entertainment, finance, communication, and artificial intelligence. But here's the fascinating part. The entire technology revolution relied on one major trend continuing forever: faster chips, smaller transistors, more computing power. But the problem is nature may finally be pushing back against that trend. One of the most famous ideas in computing history is something called Moore's Law. Back in the 1960s, Intel co-founder Gordon Moore noticed an interesting pattern. The number of transistors on computer chips seemed to double roughly every couple of years, and surprisingly, this prediction stayed accurate for decades. That meant computers kept becoming exponentially more powerful over time. Think about how unbelievable that really is. Technology companies repeatedly manage to shrink billions of tiny components while increasing performance generation after generation. That's why old computers now feel painfully slow compared to modern devices. Moore's law helped derive and drive the digital age forward. But here's the important question: what happens when transistors become so tiny that they can barely shrink any further? Engineers are now working at scales too small that they are approaching the size of individual atoms. At that level, strange physical effects begin appearing. Manufacturing becomes incredibly difficult, cost rises dramatically, and suddenly the steady progress that powered modern computing starts slowing down. That's why many experts believe Moore's law is no longer advancing the way it once did. For years, the solution to faster computers seemed simple. Just make everything smaller. Smaller transistors meant more processing power, but eventually engineers ran into a serious challenge. At extremely tiny scales, physics becomes difficult to control. Imagine trying to build microscopic electrical pathways smaller than things you cannot even see with normal microscopes. As transistors shrink, electrical leakage becomes more a problem. Heat increases, stability becomes harder to maintain, and manufacturing these advanced chips becomes incredibly expensive. Think about this situation. Technology companies are spending billions of dollars creating tiny improvements that once came easily. And even after all that investment, performance gains are no longer growing as rapidly as before. This is one reason why your smartphone today may not feel dramatically faster than last year's model. We are reaching a stage where classical computing improvements require enormous effort for smaller rewards, and this creates a major problem for the future because the world's demand for computing power is not slowing down at all. In fact, it's accelerating faster than ever before. One of the biggest hidden problems inside modern computers is heat. Every calculation performed by a processor generates energy, and much of that energy becomes heat. Now imagine billions of transistors switching on and off continuously inside a tiny chip. The result is enormous heat generation. That's why gaming computers need giant cooling systems and why massive data centers consume huge amount of electricity just to stay operational. Here's something interesting to think about. Some advanced AI data centers now consume electricity comparable to small cities. And as artificial intelligence systems grow larger, energy demands continue rising rapidly. Heat is no longer just a technical inconvenience, it's becoming one of the biggest limitations in future computing. Engineers can build more powerful processors, but eventually cooling and energy efficiency become serious obstacles. This challenge is especially important for technologies like artificial intelligence, where enormous computational workloads run continuously for days or weeks. And this growing energy crisis is one reason researchers are exploring entirely different approaches to computing, including quantum computing. Artificial intelligence is one of the biggest reasons classical computing is under pressure today. Modern AI models process unbelievable amounts of information. They analyze language, images, video, scientific data, financial systems, and even medical research. But training these systems requires massive computational power. Think about this. Some advanced AI models are trained using thousands of powerful processors running continuously inside giant data centers. The amount of electricity, cooling, and hardware required is enormous, and the demand keeps increasing every year. Now, imagine future AI systems becoming even more advanced than today's models. The computational requirements could become overwhelming for traditional systems alone. Researchers are already asking an important question. Can classical computers continue supporting future AI growth efficiently? This is one reason why quantum computing is attracting so much attention. Scientists believe quantum systems may someday help solve certain types of problems more efficiently than classical computers. That doesn't mean quantum computers will replace traditional machines completely, but they may become powerful partners for solving extremely complex computational challenges in the future. So, Now we arrive at a fascinating moment in technology history. Classical computing is still incredibly powerful, but the rapid growth that once defined the industry is slowing down. Improvements are becoming harder, more expensive, and more energy intensive. Meanwhile, humanity's computational demands keep exploding. Artificial intelligence, climate modeling, cybersecurity, scientific simulations, and future technologies all require more power than ever before. This creates a major question for the future. If classical computing eventually reaches practical limits, what comes next? Researchers around the world are now exploring alternative approaches. Some focus on specialized AI hardware, others explore neuromorphic systems inspired by the human brain. And then there's quantum computing, one of the most ambitious technological ideas humanity has ever attempted. Quantum systems do not process information the same way classical machines do. Instead of relying only on bits, they use qubits and quantum mechanics itself. And that completely changes how computation works. Quantum computer matters because researchers believe some future problems may simply become too difficult for classical systems alone. Quantum computers approach computation differently by using qubits, superposition, and quantum behavior to process information in new ways. Now imagine this situation. Instead of checking one possibility at a time like classical computers often do, quantum systems may explore many possibilities simultaneously for certain tasks. That could become incredibly valuable for fields involving massive complexity. For example, drug discovery, climate situations, optimization, artificial intelligence, cybersecurity, and scientific research are all areas where quantum systems may eventually provide major advantages. Of course, quantum computing is still developing. The technology remains experimental, expensive, and difficult to scale, but governments, universities, and technology companies worldwide are investing billions into this field because the potential impact could be enormous. We may currently be witnessing the beginning of the next major computing revolution, and just like the internet transformed the world decades ago, quantum computing could eventually redefine what computers are capable of achieving. Classical computers transformed human civilization. They powered the internet, smartphones, artificial intelligence, scientific research, and nearly every modern technology we rely on today. For decades, Moore's law allowed computing power to grow rapidly as engineers packed more transistors onto smaller chips. But now, as summary, the industry is approaching serious physical and engineering limits. Transistors are becoming incredibly tiny, heat generation is increasing, energy demands are exploding, and modern AI systems require enormous amounts of computational power that continue growing every year. Think about where technology is heading. Future artificial intelligence, medical simulations, cybersecurity systems, climate modeling, and advanced scientific research may require computational capabilities far behind what traditional systems can effectively provide. That's why researchers are now exploring entirely new approaches to computing. Quantum computing is one of the most exciting possibilities because it changes how computation itself works. Instead of relying only on classical bits, quantum systems use qubits and quantum mechanics to process information differently. While practical quantum computers are still developing, the motivation behind this research is becoming clearer every year. The world's demand for computation is accelerating faster than classical computing improvements alone may be able to sustain, and that may eventually push humanity into a complete new era of computing technology. In the next video, we will explore qubits and why they behave completely differently from normal computer bits. Subscribe now and let's continue exploring the future growth together.